you'll never see this video. Hello and welcome to Thursday's edition of Cracking the Cryptic, and thanks to Jovial for that version of Mozart's Sonata No. 16 that you heard in the title there. That might have the composer himself spinning in his grave, I suspect. Nori Nori. Now today's puzzle on screen now is by Mesmer. And Mesmer has appeared on the channel before, but not for a while. I think it's about a year since Mesmer last made an appearance, and this is a daunting looking and fascinating sounding Sudoku. Indeed, it has a very unusual rule set, and I have read the rules and I'm wondering how on earth I'm going to start this. So I'm hoping my subconscious brain is ticking this over so that when we actually kick off, I will have a clue what to do. It gave a couple of the testers an awful lot of trouble. So yeah, this could be a long video. Now, anything to mention before we start? Yes, just if you have not attempted our Wonders of the World Sudoku hunt, which is available on Patreon at the moment, then please do so soon. We're continuing. Mark's been listing all the names of the successful solvers, and we have now created our solution video for that. So that will go live on Patreon. It won't be today or tomorrow, but it will be soon. So if you do want to submit a correct solution, do try and do that in the next 2 or 3 days, I think. There's loads of other stuff over on Patreon, obviously, at the moment as well. Do have a look if you've not had a look over there. Now, what are the rules of Mesmer's puzzle? I shall read them to you. We have got normal Sudoku rules apply. Digits cannot repeat within a cage. The value of a cage is the sum of the digits it contains. Well, there's no surprises there. The value of any cage must appear only once on the board. E.g., if a cage value is determined to be 15, there is not another cage with the value 15. Okay, so each one of these cages adds up to a different number. The inequality sign is pointing to the smaller digit of the two cells. That's okay, so this square is smaller than this square. The cells on the diagonal the arrow is pointing to, that must be this arrow, sum to double the value of the cage marked with X, which is this cage. So you add up that cage, and then this diagonal here must add up to double those 3 squares. And digits can repeat on the diagonal, so no surprise there. So literally we get an inequality sign, an X, a 2X, and the knowledge that these are all different values, and that's it. Wow. Okay, do have a go. The way to play is to click the link under the video as usual. Now I get to play. Let's get cracking. And I really am not sure what to do here. Are there any uncaged cells? There's that one I can see. That one. So we've got 2 uncaged cells. The rest of the board is covered in cages. Have we got any unusually large cages? I can't actually see any large cages at all. They all seem to be 3 cells. There's a 2 cell there, a 4 cell here, 4 cell there, 2 cell. Oh, okay, there are quite a few of other, but I'm not finding any big cages. There's another 4 cell there. How many 4 cells have I got now? 1, 2. I've got 4 cells, another 2 cell. Is that it? So the rest of them are 3 cell cages. Okay, well that is interesting because there can't be that many digits that you can make. You can obviously make a cage add to 6 with 3 digits, and you can make a cage add up to, on the other side, 24 with 3 digits. So with 7, 8 and 9 you make 24, with 1, 2 and 3 you make 6. So I'm just wondering if we've got the whole complement of digits between 6 and 24 inclusive here. So maybe I'll just I'll highlight. You know I love my colours. I'm going to highlight the cages that are not 3 cells, and let's count how many 3-cell cages we've got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So that's right, isn't it? That is right. So 24 minus 6 is 18, but if we include both boundaries, we get 19. And I think that's right, because if we had 2 cages, a 7 and a 6 cage, then there would definitely be 2 cages, or there would be a 7 and a 6 cage. But if we deduct 6 from 7, we get the number 1. So we always have to count the boundary basically for one more. So 19 is very interesting. So that basically means every single 3-cell cage must be a unique value between 6 and 24 inclusive. Right, and that means the 3-cell cages must be 3, 4, and 5, because you can't make a 3-cell cage add up to 25, and you can't make it add up to less than 3. So these are 3, 4, and 5, and these ones, the 4-cell cages, have to be some number between 25 and 30 inclusive, because you can't make 4 cells add up to more than 30. So we have actually got a bit of a restriction going on here. Oh, please don't tell me I'm not going to have to... I've just had a horrible thought. Do I have to add up? Oh dear. Now I'm wondering. Now, okay, let's ask a question. And this allows me to impart a secret to you. What does an entire Sudoku grid add up to? If we looked at the finished solution to this puzzle and added up every single cell, what would we get? Well, we can work that out, because in any row of the Sudoku, we'll get all of the digits from 1 to 9, obviously, once each. If you add up all the digits from 1 to 9, you get 45, which is my secret. So 45 times 9 is 405. So the whole grid adds to 405. Now, we now know that all of the green squares plus the 2-cell purple squares, we know the values of those. So that's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Now, what do they sum to? That's a slightly rhetorical question. We can work that out by pairing them off, actually. So if I add, let's sum the digits 1 to 24. So that's going to get too high, but it's only going to get too high by 3. So because 1 plus 24 is 25, and 23 plus 2 is 25, and 22 plus 3 is 25, we can basically say that the sum of the digits 1 to 24 is 12 lots of 25. And I can do that, that's 300. So 300 minus 1 minus 2 is 297 for all the green squares plus the orange squares. 297, and I know I'm heading for 405, so I need 108 in the remainder. And these 4 squares have to be at least... well, they have to be at least 25 each, so that's going to give me 100. But they can't all be the same. So if we go 25, 26, 27, 28, we would have 106 plus 297 is 403. So that must be what they are, because we cannot go higher than that, or we won't have enough gap to allow these squares to have a positive value. So these are 1s, and the 4-cell purples, maybe I'll make those a different colour actually. The 4-cell purples add up to 106 and are 25, 26, 27 and 28. Phew. Now we might be able to make some progress, because we can make progress. What's this cage? This is a 2-cell cage. It adds up to 3, 4 or 5. Well, if it added up to 3 or 4, it would need a 1 in it. It's definitely not got a 1 in it, so this is a 2, 3 cage. Which means both, this is lovely, both of these cages have to contain a 1 now, and we know where the 1s go. So we get a start, look. And these squares have got to be 2 or 3, depending on which one of them is 3 and which one of them is 4. When we can do Sudoku, look, and get a 1 here. And this cage is now forced to be 25, because we know it adds up to more than 24, and the only way we can get to 25 is with 7, 8, 9 in the box, in the cage, sorry. So this is a 25 cage. Oh goodness, I'm just thinking, how on earth am I going to keep track of which numbers I've got? Because it's all very well at the start knowing this is a 25 cage, but at some point I'm going to have to know, oh, I've got rid of a 19 cage, I've got rid of a 14 cage. That is going to be, I might have to use a notepad, I think, for this one. Now, what on earth do we do now? Right, I can make a bit more progress in box 5, can't I? That's clever, because by Sudoku, this cross is not the digit 1. I can't put 1 in a 4-cell cage again. I've already put 1 in one of them, and if I put another 1 in another one of them, we know that I can't repeat the 25 total, and I can't make it 26 because I can't put 8, 8, 9 in there, for example. So we've got, oh look, this is what this inequality sign is doing. Right, look, straight away at the start, 1 therefore in box 5 can't go in any of those squares. So it's in one of these 2 squares, and it can't go here. Because 1, we'd have to put 0 in there, and that won't work. So I think 1 goes there. Which means 1 is in one of those 2 cells. 2, 3, 4, 5, 6. 1 has to be in one of these 2 squares in box 6. But we can fix that by virtue of box 9, because we can't put 1 in a 4-cell cage again. So 1 is in one of those 2 squares, which means it's not here. This is a 1. And we've now got 7 1s in the grid, and a little sort of X-wing on 1s at the bottom that we've not figured out. And now I'm very tempted to look for the 6 cage, I have to say, because I can see this can't be a 6 cage. A 6 cage obviously has to be 1, 2 and 3. Well, we can't put 2 and 3 in there because that will break this square. This can't be 1, 2 or 3. Yeah, okay, so the 1, 2 and 3 is not this one, it's not this one, it's not this one. It's not this one because that puts 2, 3 here. It's not this one, it's not this one, and it's not this one. So it's one of these, well, it's one of these 2 1s, but they are in 3 different boxes. This one's impossible, because if we put 1 in there, these would have to be a 2, 3 pair, and then you get a repeated 2, 3, either in column 8 or in box 6. So that is not the 1, 2, 3 cage. This is not the 1, 2, 3 cage for the same reason. If this is the 1, this square would have to be a 2 or a 3, and it breaks column 8. So this, I think, is the 1, 2, 3 cage, if that's right. That's not 1. Now what do we do? More Sudoku on this box? We've now got... We've now got to put 2 and 3 into these squares. Well, if they were up here, that would be useful because we would know the order. Don't know. I'm not sure. Oh. No. Actually, there is more I can do here. Sorry. Look, let's think again about this central box. I can't put 2 or 3 here, and I can't put 2 or 3 here. Now, I also can't put 2 and 3 in these 2 squares, because that will leave this square with no option. So this square is a 2 or a 3. And it's not a 2, because if it's a 2, this would be a 1, and that will break. That's a 3, and therefore that's a 2. This is ridiculously clever. That's a 3. This is now a 4 cage, so this must be a 3 cage. That's a 2, that's a 2, that's a 3. And all of a sudden, I've actually got quite a few digits now. Now, I can see that 3 has to be in one of those squares. I'm not sure if I'm meant to be able to see other things I can do in this box now. I presume I don't use this anytime soon because, no, I can't. I mean, this 2x thing feels like, I mean, we are almost going to have to know the whole of this diagonal for that to be interesting. Okay, so what have I got? I've got cages 3, 4, 5, oops, 6. I need 7. So 7 must have a 1. Actually, 7 and 8 must have a 1 in them. So maybe that's what I've got to do. Do I have to keep going upwards? Yeah, okay. Yes. Well, that can't be... Yes, this cage can't be 7 or 8. Because if it's 7, it would need 2 and 4 here. If it's 8, it would need 2 and 5 or 3 and 4. Both are impossible. So I'm getting confused now. This one can't be 7. But it could be 8 if 8 was 1, 3, 4. So this could be 8. But not 7. Maybe that's what maybe I've got to look for 7. Yeah, I have. I see. If I look for 7, 7 is not here. 7 is not here. So 7 has to be one of these 2. Now it can't be this one, because if this was 1, you'd have to put 2 in one of those squares. So this, I think, is 7, which means this is 4. This is 1, and this is 2, and this is 3. And this is, look at that, it just fills in. Now we look for 8. Now, 8 is either this one or it's this one. Oh, but it can't be this one now because I can't put 1 in here. I see. So it's this one, and it must be 1, 3, 4, and it must be like this because it can't be 1, 2, 5. And actually, we've got more digits as a result of that. So I've now done 3, 4, 5, 6, 7, 8. So I need to look for 9 next. That can't be 9, even though there's a 1 in there. It's not possible to put useful digits in that domino, look, because 2 and 3 are unavailable. The minimum I could make this cage would be 10 with 4 and 5 here. So 9 has not got a 1 in it. So 9 must be a 2, 3, 4 cage. This is crazy. So it's a 2, 3, 4 cage we're looking for. And Does that mean we know where it is? 2 has to be on the right hand side of box 4 has to be on there. I'm not sure whether I'm meant to be doing Sudoku or looking for the 2, 3, 4 cage or something else. 3, 1, 3, 1, 2. Sort of feel like I can put 3 here. Oh no, I can't. I can put 3 here. It means 3 is up there. This square, I don't... Oh, no, hang on. 522, that's not big enough. Right, this 4-cell cage has got a 3 in it. So it can't also have a 2 in it, because then the highest I could make it would be 22. And we know this needs to add up to at least 26, I think. It can't be 25, because that one's 25. There's no 2 in that cage. Given there's a 3 in it, there's no 2. So this is a 2. This can't be our 9 cage, though, because we couldn't put 3 and 4 into it. So 2 is in that cage. No, this can't be our 9 cage because you can't put 3 in it. 2 is in one of those squares as well. I feel like I might be able to do more with 2s. 2s are in one of those squares. Maybe that... Oh no, this can't be 2, 3, 4 because that square can't on its own be 2, 3 or 4. Right, okay. I've decided. I am going to look for the 2, 3, 4 cage. Now... Which one is it? Could it be this one? 3, 2, 4. Yes, maybe. I think this one could be it. Right, let's highlight that one as possible. I'll make it black. This one can't be a 2, 3, 4 cage because 3, you can't put 3 in it. This one, you can't put 3 in. So this is not a 2, 3, 4 cage. This one may be. No, you just can't put 3 in it at all. Same with this one. So maybe I should be highlighting the ones it can't be, actually. Maybe that would be better. What about, no, that one can't be. That one can't be. This one, no, you can't put 2 in that one. This one you can't put 4 in. This one you'd have to put 2 and 3 in this square, so that doesn't work. This one, no, this one's ruled out by this 2, 3, 4 triple over here. That one's already been ruled out, doesn't add up to the right number. That one we can rule out. This one can't have a 2 in it. This one can't have a 2 in it. This one sees too many 3, 2s and 4s. This one can't have a 2 in it. Right, I think it's this one. Right, this is 3, 2, 4 and we can fill it in. Wow, 3, 2, 4 go in. That means that's a 2. I can get rid of the highlighting, I think. I don't think we need to keep that as highlighted. Now, 2, 4. Now, let's have a think about this then. These two squares are a 5, 6 pair just by Sudoku of all things. Fancy doing Sudoku in a Sudoku puzzle. Now, this 2 is ruling a 2 out from that square, so there's a 2 here. How many 2s have I got? Oh, all of them, in fact. I've done all the 2s. I've done all the 1s. I've not done all the 3s. Right, 3s. Oh. Yes. Look, where do I put 3 in this box? It's got to go there. That means 3's in one of those 2 cells. Okay, so I've now done 7 3's. I've got an X-wing on 3's left. 4's. I can see 4 has to be in one of those 2 positions. And one of these 2 positions. This is a domino that has to contain a 4. I think we're running out of the road with that though. Okay, so what do we do now? I guess we've got 9. We must be looking at 10. 10 or 11, I suppose. Now I've got a spare 1 here that could be useful for that. I'm just not sure if there's an efficient way to do this. Is there something I can say about... Well, yes, there is. If I'm looking for 10 and 11, we know 3 plus 4 plus 5 adds to 12. So any 10 or 11 cage must contain at least a 1 or a 2 or both. So we're only looking for cages that have 1s and 2s in them, and we have identified all of those cages. So this cage could be... No, it could be the 11 cage. No, it can't actually. Sorry, no, this square's got a minimum value of 5. 5 plus 6 plus 2 is too many. So this cage is not the right cage. This cage has not got a 1 or a 2 in it, so we can immediately dismiss that. Right, this cage. No, this cage is too big. It's going to have 5s and 6s here. This cage is too big because it can't have 1 or 2 in it. This cage can't have 1 or 2 in it. This cage... I know that cage could have... This square is possible. That one I think is interesting. This one here. This one has not got 1 or 2 in it. I need one... this one maybe? Can't see why this couldn't be a 5, so I think that one is definitely on the cards. This one can't be, it can't have 1 or 2 in it. This one I've looked at, I should have highlighted the ones that can't be. This one here, that could be 4 and 5, so this one can be. This one can't be because it can't have a 1 or a 2 in it. So we know that the 10 and the 11 have to be in 2 of the 3 red cages. So if this was... what have we got at the moment? 50. No, this is lovely. I see. This square cannot be a 5 or a 6. Because if it is, this cage has to be 29 or 30. We've got 10 there at the moment. So these squares together have to add up to 35. Well, if we make this a 5 or a 6, then this is 30 or 29. We know that the orange squares are 25, 26, 27 and 28. So this red one is impossible to be 10 or 11. So we can change the colour of it back to green. These two have to be... So this must be a 5 or a 6. This... we know this is either... this is interesting. So this one has to have a 4 in it. Because if it doesn't have a 4 in it, it would be 1, 5 and 6, and that adds up to 12. So if there's a 4 in it, it's here. And then this square is either a 5 or a 6. So there is a very peculiar 5-6 pair sort of in those two squares. So this square, for example, can't be a 5 or a 6 because it sees those two and these two are different. So that square... well, that's actually, I've just seen that's a 4 now as a result of this being a 4. But this square can't be 1, 2, 3, 4, 5 or 6. So this is a... oh, look, this is a 7, 8 or a 9. That gives a triple in row column 1. So this square is a 5 or a 6. Okay. Do we know the order of this? This square, I suppose, is the same logic. This square can't be 5 or 6 because it sees both of those. And this one can't be 1, 2, 3 or 4 either. So this is also 7, 8 or 9. which doesn't seem to be that helpful. Okay, so what do we do now? This has got 3 in it. Can I do something with that? Do I therefore know the value of this 4-cell cage? Is it possible this has a 4 in it? 3 plus 4 is 7, plus 8 plus 9 is 24. That's not big enough. There's no 4 in this cage. Right, look, that means, in fact, that's lovely. There's no 4 in this cage. Where do I put 4 in this? Yes, where do I put 4 in box 3? It can't go in any of those squares. Can't be here, can't be here. It's there. Therefore, this is 4. Whoa, I'm pressing the wrong thing. I'm always terrified when I press an F button when I'm in the middle. I think hopefully that hasn't just broken the puzzle. Rather than a digit. That's a 4. Okay, that doesn't seem to have done a lot more. So now I still don't know what this is though, do I? It's 26. I know it's not 28 because I can't make it add up to 28. If it's 27, it's... Oh no, I do know. It can't be... Yes, I do know. Look, if this added up to 27, this cage would have to contain 3, 7, 8, and 9. Well, look now. That means I've got to make these 5 cells be just 4 different digits. That's not going to work. So we actually know that this is the 26 cage, and therefore we know it's got 3, 6, 8, and 9 in it. And now we can ask where 5 goes in row 1. How long must it take to create a puzzle like this? I mean, this is just, it's born of sheer genius, isn't it? It's quite extraordinary. 7 now has to be over there. This is not 7. 3 is not here. This is not 3. It sees 3 as well. No, I'm not seeing much else. I suppose now I know those 2 squares have got to be a 5, 7 pair. Just to complete the box. So we almost know the value of x now. We've not put 5, 7, 8, and 9 into this row. So if this is 5, this is 7, 8, 9, which is 24, and then this diagonal here would have to add up to 48. And if this is a 7, this would be 5, 8, 9, which is 22, so this would add up to 44. Right, okay, so there really isn't much difference between those 2 digits. We know this is a pretty, well, we know it's 40 something spread over 7 cells, so actually it's not terribly interesting. It's very slightly averaging on the high side. Okay, right, let's get back to it. So I haven't done, but I know approximately where 10 and 11 go. I've not found 12. So 12 and 13 are going to be the next interesting digits. Now this one, which we knew had the possibility of being 10 or 11 before I thought about this cage. Hang on, sorry, I just want to come back to the 4-cell cages. I've now got 25 and 26, so this is 27 or 28, and so is this. So if this is 27, plus 10 is 37, this would be an 8. This is 28, this would be a 7. So this is 7 or 8. So this cage is 12 or 13. And down here, we've got 7. 7 plus 27 is 34. This would be 11. This is 28 on the other hand. 35, this would be 10. Okay, I'm not sure. Okay. So either a 12 cage must contain a 1 or a 2, or it's a 3, 4, 5 cage. So can we find cages that can be 3, 4 and 5 in this grid still? I'm very sceptical about that. This one? No, you can't put 4 in it. This one you can't put 3 in. This one you can't put 3 in. I'm not sure. Is there a cage in this grid that you can put 3, 4, 5 in it? This one can't have 3 in it. This one can't have 3 in it. I don't think so. At least I'm not seeing it. So if you can't put 3, 4, 5 in it, it must contain a 1 or a 2. And that limits the options. That means there's this one, this one, this one, 3 I think. I think there are just 3 cages that have the possibility of adding up to 12. So if it's this one can't. That would have to be a 5. That one we can get rid of immediately. This one's going to be the same, isn't it? This square just, if this is 7, this has to be 3. That breaks. If it's 5, you have to double the 5. So I think the only cage that can be 12 is this one, which means this is a 7. Which actually doesn't seem to do much. It will tell us what this cage is, though. We've now got, this is the 28 cage. So this cage is 5, 6, 8, 9. Which means this is the 27 cage. But we don't know if it's got a 3 in it or not. Right, so... But it's 27 plus 7 is 34. This domino adds up to 11. Don't really have a good way of pencil marking that. 11. Does this 7... this 7 locks a 7 into one of those cells. 7 is in this domino up here. Six is in one of those 2 squares, look. So 6 is not in that square. Ooh, I've got an 8, 9 pair in row 2 now. So these squares are 5, 6 and 7. That one can't be 7. This can't be 5, of course, because that would repeat the 5. So this is 6. This puzzle is... How did you set this? This is just... It's unbelievable that this can be set and have a smooth path like this. Now this cage is a 13 cage. That was the next number I was going to look for. We found it. 13 we found. This one we know is 16. Oh goodness, this is where it's going to get impossible. So we found everything to 13. We found 16. When I say everything, I mean I know these are 10 and 11 and we don't know the order, but we do know roughly where they go. So we're now looking for 14 and 15 basically. Is there anything else we can say? Just excuse me while I think about this before we plough on trying to find the 14 cage. I just feel like there might be something we can we can get more straightforwardly. 6 in column 6, look, it's not here, so it must be in one of those 3 squares, so it's not in the central square. This square, no. Right, so let's look about the 14 cage. What do we know about a 14 cage? We know a 14 cage must contain a 1, 2 or a 3, because a 4, 5, 6 cage is 15. So we have to find a cage that has the ability for us to put a 1, 2 or a 3 into it. Now there can't be that many more of those left. There's this one down here. So this cage is a chance. Look, these 1, 2 and 3 in here basically rule out a lot of, yes, lovely, all of this gets ruled out. This one, no, because that square cannot be anything. These two can't be. So it's either this one, can't put 1, 2 or 3 in this one. That one, that has got a 2 in it and is still open to question. It's going to be so easy to make a mistake though, and just if I miss a cage, the whole of the logic will fall apart. I can't see another one, so it's one of these two. And if it's this one, this would have to be a 3. Ah, no, this one doesn't work, does it? Because if this is a 3, we know that domino is adding up to 11, because we worked out that this had to be... I'm getting confused now. This was the 27. 27 plus 7, 34. This is 11. So if this is 3, that has to be 8. And now, how are we going to make this the right digit to give us 14? We can't put 3 in again. That won't work. So this is not the 14 cage, which I think means this is the 14 cage, which means these add up to 12, so this is 5 or 7. We've got a weird 5, 7 thing going on. So in this column, these squares here are 6, 8 and 9. I don't know much about 6, 8s and 9s though. Oh, but I suppose we know this domino adds up to, yes. Ooh, this is not 9, because that would put 2 here. Oh, bobbins. So this is 3 or 5. Both seem possible. There's a little trick you can do with colouring here. This square can't be a 5. I admit it's the tiniest of deductions, but that's as good as I've got. Look, because whatever this square is, doesn't matter if it's 5 or 7. Let's imagine it's 7, just for the sake of exposition. If this is 7, this will be 5, this will be 7, and this will be 5. So the point is that these two are different. And if these two are different, any cell that sees both of these squares can't be a 5 or a 7. And this square sees both of them, so it can't be a 5. So 5 is in one of those. 5, 6, 8, 9. This square is 5, 6, 8, 9. Can we do something similar with this one via 5s? Yeah, again, this square can't be a 5 because this time these two would be the same colour. And if this is 5, this will be 5, and now you can't put 5 in that cage there. So this square is down to 6, 8 or 9. Again, completely useless. Right, okay, what did I just find? I found the 14 cage. So the next one is the 15 cage. Where is that, and what can we say about it first? We can say 15 could be 4, 5, 6. So perhaps a better way of asking the question would be, is there a cage available that can have a 1, 2 or a 3 in it and add up to 15. This one, is this the only cage left that could be that could have a 1, 2 or 3 in it? Is that wrong? It's not wrong, is it? This is the only cage left on the board that could contain a 1, 2 or a 3 and possibly be a 15 cage. So if this is a 3, it doesn't work. You can't make those two add up to 12. So this is not a 15 cage. At least it's not a 15 cage with a 3 in it. So the 15 cage in this puzzle is a 4, 5, 6 cage, and that might be good enough for us to hone in on it. We need a 4. Oh, no. I don't think that one can be 4, 5, 6. Look, because this can't be anything useful. This one, no, that can't be 4, 5. I'm trying to do this slowly. What about that one? No, good grief. This one can't be, because if this was a 5, 6 domino, that would have no value. So it's not this one. We know it's not red. This one. This one would have to be 5, 6, 4, which it can't be. Wow. Okay. This one. 4 would have to be here. 5, 6 domino. That one might be possible. Can't see immediately why that one isn't possible. What about this one? No, this one can't be. You can't put a 6 in this cage at all. So 4... So 4, 5, 6 could go here. It can't go here. About that one then. 4, 5, 6. Oh, that would have to be 4, 5, 6. Oh, bother. I think this might be possible. So it's one of those two. That was 4, 5, 6. It all gets very complicated. If this is 4, 5, 6, I don't know. I'm not sure. Sorry about this. I think it's one of those two, but I don't think I know which one. That's rather going to break the streak, isn't it? 6 I can see has to go in one of those cells. Okay. Maybe I should be trying to work out which of these cages can be 7, 8, 9. Which is the big cage? I've not really thought about that yet. But actually that's going to be easy, isn't it? Because I've just got I have got some 7s, 8s and 9s. That can't be. But I think cages like this and this, I think could still absolutely be 7s, 8s and 9s. In a funny way, 6s are more restricted than 7s. So maybe 23 is a harder digit to get to. This could be 6, 8 and 9. But apart from that, what other cage can be 6, 8 or 9 other than this one? I'm not seeing anything. This one, can that be 6, 8, 9? Maybe it can. So this one or this one? That one can't be. That's interesting. That can't be 6, 8, 9 because that will clash with this square. This one can't be because you can't put 6 in it at all. That can't be. That's right. Okay, look at that. So 6, 8, 9 is either here or here. So it's definitely in a cell that is poking in to box 4. Either here or here. I tell you what might be hard to do. If this is 6, 8, 9, that's going to force that to be the 12 cage, and that will have to be 4, 5, 6. Broke. Yeah, that's it. Beautiful. That is absolutely beautiful. So you can't do this. The 23 cage is in one of these two positions. If it's here, we know that the 12 cage is there. And we know that the 12 cage is a 4, 5, 6 page. And if you look at this, where does the 6 then go? If this is the 12 cage, it's got to go here. So this is going to be a 6. And now you can't put a 6 in here. In fact, you can't. So this can't be 6, 8, 9. It's impossible because you can't put a 6 in the cage. So this is the only place that we can find the 23 cage, and that gives me a 7. And another 7. Good. 2 digits. We're not going to complain about that. And 3 digits. That's a 6. Is that as far as we can go with this? Don't know. This row, you can see this square here has to be 5 or 7. Oh no, this is good. Right, okay. So now in column 7, I've got a 5, 7 pair. That's fixing this as a 3. We now know that this is domino adding up to 11, so we get another digit. This is an 8. So that's not 8 at the top. We can remove 8 from those two squares. That's... And I suppose we now know... Let me just double check this. What is this? So this is 5, 6, 7 and 9, which is adding up to 27, which is correct. That is the missing digit. Okay, so 5, 6, 7 and 9 into those squares. Now that looks very interesting in terms of this column, doesn't it? Because now I've got 5, 6, 7, 9 quadruple, which means this square must be an 8 and this square must be a 3. So we can get rid of 3 and 8 from that cell. We get a 6, 9 pair here. That fixes this 8, 9 pair at the top. This square here, I feel like I've got too many digits left in this puzzle now in terms of this column seems, I mean, this being a 6, 8, 9. No, the 5, 7, that's why I'm getting confused. This does feel wrong because that should be a 6. Now that had a pair over here. So this is the 11 cage now. So this is the 10 cage. That gets us another digit. That removes a digit from here. It means this square is a 5, I think, to complete this box. Therefore this is not 5. This square is an 8 or a 9. It's not 8 because it would repeat in the cage. So it's 9. This is a 20 cage. This is an 8. Whoopsie, I did the wrong thing there. That's a green cell that I want to make an 8. This is an 8. This is a 5, 9 pair. Now, can we keep going? Keep going? Yeah, we can. 9's at the top. 9 and 6 go into the grid. Still don't know what X is, do we? But we might be... This 6 places a 6 at the bottom, of course. Sorry about that. Should have done that immediately. Oh, but 6 here means that can't be a 4, 5, 6 triple. So this is not the 15 cage. So we can turn it green. This must be the 15 cage. So this is a 4, 6 pair. You can see where the 4 has to go. 6 goes here by Sudoku. 6. So these squares, in fact 4 goes here by Sudoku as well. And these 3 squares here have to be a 7, 8, 9 triple. And that's not 7. And we must be very close to finishing it, I think. 5, 8 and 9 into these squares. Let's label everything up and see what we can see. 5, 8, 9 here. So this is 5, 7 or 9. Oh dear, and this has lots of options. 5, 7, 8 or 9. I'm going to end up with a fully pencil mark grid, aren't I? I think so. 5, 7s, 8s and 9s here. Obviously I can get rid of 8 from that square. Oh dear. Right, okay. So what can we do now? Do we know what that is, for example? That, we've got 12. So this is 17 or 19. I've totally lost track in terms of what we've got in the grid. So maybe I should just do a quick audit of new... See, we've got a 20 cage there that I've never really thought about. We've got that one. I think I did look at that one earlier. That's 11. No, that's 11 plus 2 is 13. This one is 16. That one's 14. That one was 17 or 19. That one's the 23. I do remember that one. That's the 12. This one is that one's a 17. That one is a 17. Don't know when that appeared, but that means this one can't be 17 as well. So this must be a 7. We get another, or we get a flurry of digits, in fact. Look at that. Oh, that's going to fix... Yeah, hang on. Now we now know what X is. X is 22. So we now know that this diagonal is a 44 diagonal. And at the moment we've got 23. So these have to add up to 21. Oh dear, that doesn't actually look brilliant, does it? Bother. Okay. Do I really have to wade through the possibilities here? Always going to have a 5, then a 7 or a 9 in either order. What digits have I not filled in? Because we must have got... We've got 22 now. We've got 23. I think I saw 20. I did see 20. I've not seen... Have I seen 19? I'm not sure if I've seen 19. I've not seen 24. Actually, I've not seen 24. Oh no! No, that one. Can that be 24? Oh, thank goodness for that. That can be 24, and I think has to be 24. Oh, good. Right, this one is 24. It's the only place 24 can go. 9, 8, 7. Gives us an 8-9 pair here. Gives us a 9 here. 8, 9 gives us a 5 here. That gives us a 9 here, gives us an 8 here, 9 here, 5 here. Oh, you can see, I can totally understand how Mesmer has set this puzzle, well, at this very late stage. I've no idea how he did the first part of it, but look how he's selected this diagonal. We're left here with 2 deadly patterns, 5s, 7s, 8s and 9s. And this diagonal actually disambiguates both. So what do we need? We need 44 on this diagonal. We've got 24 plus 7 is 31. So we need 13 from those 2 squares. And there's only one way of doing that. And it's going to disambiguate both deadly patterns and finish the grid. That's going to have to be 5. That's going to have to be 8, 9, 9, 8, 7 here, 7 here, 5 here. That is magnificent. Absolutely magnificent. That is a rare puzzle indeed, incredibly intricate setting, and actually a complete pleasure to solve, and but not easy. Certainly the stuff I had to do with the what was it? The 23 cage and the the 15 cage. So the 23 and the 15, and how you disambiguated those was really intricate. And there may have been a better way of doing that, so you will have to let me know in the comments. I do enjoy reading them, especially when they're kind. Thank you so much for watching, and we'll be back later with another edition of Cracking the Cryptic. You'll never see this video. I'm mad.